Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we're going to investigate MH370 and the unforeseen destination. How did MH370 disappear into the Indian Ocean? How is it possible for an aircraft like a Boeing 777 to simply disappear? In the modern global glasshouse of radar and satellite systems, surely someone must have tracked the aircraft. Questions have been raised regarding potential detection by the over-the-horizon radar systems and underwater acoustic systems and military radar installations. A lot of questions, but very few answers. Independent aircraft investigations brings you the established facts. We provide traceability of all evidence to a source authority. We make a clear distinction between factual data and analytical interpretation. We operationalise ICAO Annex 13, the standard for investigations into aircraft incidents and accidents. We embed investigative discipline directly into the production of each episode. This ensures factual material, analytical work, and narrative outputs remain clearly distinguished, traceable, and compliant throughout the life cycle of an investigation. Aviation news is covered on Daily Airline News with Jeffrey Thomas, as it happens. This channel is reserved exclusively for in-depth investigations. If you find this analysis useful and want to see future independent investigations, subscribing to the channel helps ensure this work continues. Some images and animations in this program are computer-generated or stock visuals used for illustration only. They do not represent the actual aircraft, crew, or recorded flight data unless explicitly stated. In the previous episode, Unexpected Diversion, we established that MH370 diverted from its flight plan and made an air turnback across Malaysia and headed out over the Malacca Strait in a northwesterly direction. The aircraft was unidentified following the diversion at 17:20:34 UTC until 18:25:27 UTC, when the Satellite Data Unit, the SDU, was rebooted, and the ICAO identifier, hex code 75008F, for the Malaysian Airlines Boeing 777-200ER registration 9M-MRO, was received via the Indian Ocean Region Inmarsat satellite and at the ground station in Perth, Australia. The aircraft remained unresponsive and there was no radio contact, and satellite phone calls and messages sent to the cockpit printer went unanswered. The standard ICAO procedure for an unidentified and unresponsive aircraft was not followed. In this episode, we will examine the physical and electronic evidence which conclusively proves that MH370 continued to fly for 7 hours 37 minutes until fuel exhaustion and ended in the southern Indian Ocean. Let's have a look first at the Inmarsat satellite data in some detail. Subsequent analysis of signals transmitted by the aircraft's satellite communications terminal to Inmarsat's 3F1 Indian Ocean region satellite indicated that the aircraft continued to fly for several hours after loss of contact, resulting in the search moving to the southern Indian Ocean. The Inmarsat satellite 3F1 covers the Indian Ocean region and has a nominal position above the equator at 64.5 degrees east. This was originally a geostationary orbit at an altitude of 35,786 kilometers, but is now 30 years since the launch, and the satellite no longer remains perfectly stationary. We have the exact ephemeris for the 7th of March 2014, so we know exactly where the satellite was positioned and how fast it was moving in all three axes, X, Y, and Z. The satellite evidence is published in the Journal of Navigation, copyright by the Royal Institute of Navigation, 2014, in an academic paper titled The Search for MH370 by Ashton, Schuster Bruce, College, and Dickinson, all of Inmarsat. In their 22-page paper, they explain how they calculate the distance of the aircraft from the position of the satellite, as well as the ground speed and track of the aircraft relative to the movement of the satellite. At 18:28:14.904 UTC, the CDU had completed its reboot and was 3,520.7 kilometers from the 3F1 satellite. So that describes the first arc and exactly where the aircraft was at a certain position along the first arc. The first arc at 18:28:15 UTC places the aircraft on a circle with a radius of 3,502.7 kilometers and from the satellite. And we know that the last civilian primary radar position was 5.582566 north, 99.183389 degrees east at 18:0051 UTC. Inmarsat, in their paper in Table 9, show an example MH370 reconstructed flight path from a point on the first arc at 6.9 degrees north, 95.8 degrees east. And this is 20 nautical miles from a waypoint called Sanob. All the way to the seventh arc, they traced then the aircraft's path. If, for example, MH370 reached the first arc at around waypoint Sanob, which is marked in green on the map we're showing, it is then a direct distance from the last civilian primary radar point of 218.435 nautical miles, and it took 27 minutes, 24 seconds. This implies a speed of 478.3 knots on a track of 286.1 degrees true. The next question is, how do we know the aircraft picked up by the Inmarsat satellite over the Indian Ocean was, in fact, MH370? We are showing the CETA raw data logs from the aircraft 9M MRO received via the 3F1 Inmarsat satellite at the ground station in Perth. The oceanic region is IOR, which stands for Indian Ocean Region. The GES ID is octal 305, which, per the Inmarsat paper cited earlier, means the Ground Earth Station 305, which is Perth, Australia, at 31.8 degrees south, 115.9 degrees east. The identity of the aircraft is ICAO code 75008F, and the code can be found in every header message. This is the same ICAO code as we show in episode 1, when we discussed the ADS-B data received from the flight identifier MH370 up until diversion and up until the transponder was switched off in the cockpit. At a point in time, according to the ADS-B data, of 62,434.55 seconds, which is 172034.55 UTC. Now, the next question, why did the pilot switch the satellite data unit, the SDU, back on 65 minutes after diversion at 1825? There are several possible reasons, and we do not know for sure why. What we do know is that the SDU is on the same power bus, the 115-volt AC left secondary 2 bus, as the Traffic Alert and Collision Avoidance System, TCAS. It is possible that the pilot wanted to briefly switch the TCAS and transponder back on to see what other aircraft were in his vicinity. There were 57 other aircraft airborne in the Kuala Lumpur FIR as MH370 crossed back over the flight information region. The next question is, how did MH370 communicate via satellite with a ground station in Perth, Australia? Radio waves travel at the speed of light from the aircraft to the satellite using the uplink in the L band at 1.6 gigahertz, and then a downlink from the satellite to the ground station in the C band at 3.6 gigahertz. Alan Schuster Bruce explained that the loss of Air France Flight 447 in 2009 prompted Inmarsat to enhance its satellite communication system, in particular by adding the burst timing offset, BTO, and the burst frequency offset, BFO, measurements to its dataset. These additional parameters were designed to help precisely geolocate an aircraft in distress, and it later proved crucial in reconstructing MH370's flight path after it lost contact. In essence, Bruce noted that the lessons learned from Air France 447 directly led to improvements in how satellite data is used to determine an aircraft's distance from the satellite. The same technology developed in response to AF 447 was instrumental in the subsequent analysis for MH370. At 1828.15 UTC, each signal from the aircraft to the satellite to the ground station traveled 76,171.1 kilometers. The last signal, on the 8th of March at 001937 UTC, traveled 77,112.9 kilometers. The satellite was 75.7 kilometers closer to the ground station and the aircraft was 1,017.4 kilometers further away from the satellite. At 18:28:15 UTC, it took 254 milliseconds for a radio signal to travel from the aircraft to the ground station. At 00:19:37, it took 257 milliseconds. That's 3 milliseconds longer because the aircraft had moved further away from the satellite. The BTO increased from 12,480 microseconds to 18,410 microseconds. That's around 6 milliseconds. So for the round trip time, 3 milliseconds in each direction. The arc on the surface increased by 1,413 kilometers, and the slant range to the aircraft to the satellite increased 920 kilometers. And the slant range round trip is therefore 1,840 kilometers or 6 milliseconds. We know MH370 headed south and ended up around 1,413 kilometers further away from the 64.5 degree east nominal position on the equator when projected onto the ocean surface. The next question, how do we know MH370 went south and not north? We can work this out from the burst frequency offset, the BFO. When we plot the BFO against time, the measured BFO fits almost exactly to the predicted BFO for the south path prediction, but does not match at all the north path prediction. MH370 is definitely in the southern Indian Ocean, according to Inmarsat. The diagram we're showing can be found in their paper at figure 14. So the second arc gets a little bit closer to the Inmarsat satellite compared to the first arc. Then MH370 turned again, and from the second arc to the seventh arc, the aircraft is getting progressively further away from the Inmarsat satellite. Now, there is one more clue confirming that MH370 headed south, and that is Singapore radar, and not terrestrial radar, but airborne radar. In the appendix of the Malaysian preliminary report, there is a Google Earth map of the assumed track of MH370. And on this map, there is a yellow pin in the diagram, which doesn't seem to belong to the rest of the graphic and is not explained in the text. It is 219.4 nautical miles from the MH370 flight path on a bearing of 303.3 degrees true. And this was a mystery until the ATSB in Australia released a 64-page report on the 26th of June 2014 and mentioned a northwest point at 1912 UTC in Appendix A, without also any further explanation. And we asked the ATSB about this information and were told the northwest point at 1912 was an assumed theoretical location at 8 degrees north, 35.719 minutes, and 92 degrees east at 35.145 minutes. and it was initially chosen to provide clearance from known radar sources, mainly from Singapore. A line from waypoint egress to the 1912 point was used as an upper bound for the airplane performance work after loss of radar contact. The minimum flight distance would be turning south right after the loss of radar, and the maximum would be this 1912 point. And this did not affect the Doppler analysis, but it did affect the fuel burn and affected the range measurements. The analysis had included these points using the upper bound as the line between the northwest 1912 point and the waypoint egress. And the lower bound was a turn south directly after the 1822 point. And it turns out that the Republic of Singapore Air Force, the RSAF, used Gulfstream G550 airborne early warning aircraft with a side-mounted active phased array radar system. The primary purpose of the RSAF G550 AEW patrols over the Malacca Strait was to maintain continuous high-fidelity air and maritime situational awareness over a vital global choke point, enabling early warning, deterrence, and rapid joint response to any security threats well before they reach Singapore's doorstep. The nominal radar range is 200 nautical miles for this aircraft, and the radar coverage from the northwest point to waypoint egress would pick up any aircraft heading north or west from waypoint Sanob. And this is further evidence that MH370 turns south towards the Indian Ocean at a point close to waypoint Sanob. Now, let's look at the fuel that MH370 had on board. The fuel docket at 1527 UTC shows there was 49,600 kilos of fuel loaded in the tanks for the flight of MH370 9M MRO from Kuala Lumpur, KUL, to Beijing, PEK, on the 7th of March 2014. Boeing calculated the fuel at takeoff was 43,800 kilos, and the remaining fuel at the first arc was 33,525 kilos. The Boeing performance analysis is included in the Malaysian official report in Appendix 1.6e. Boeing provided a table of the maximum range from the first arc based on the flight level selected and the speed setting. The maximum possible range is 2,806 nautical miles from the first arc position based on a flight level of FL 400, 40,000 feet, and a true airspeed of 469 knots, and a maximum range cruise, MRC, Mach setting of 0.818. Boeing calculate the position at the first arc as 6.676 degrees north, 95.492 degrees east. And we're showing the maximum fuel range of 2,806 nautical miles as a circle marked in red. MH370 has to be somewhere within this circle when it ran out of fuel. MH370 has to be somewhere within gliding range of the 7th arc, which is defined by the last satellite message received, also at the point where it ran out of fuel. The next set of evidence is the physical evidence from the debris. In addition to the electronic evidence from the satellite and the physical evidence of the amount of fuel, there is further physical evidence from floating debris, which has been found washed up on the shores of islands in the Indian Ocean, as well as the east coast of mainland Africa. The first item found was a flaperon from the right wing on Reunion Island. The item weighed 40 kilos and was 2.32 meters by 1.26 meters. That's 7.6 feet by 4.1 feet. The item was confirmed from unique identifiers to be from flight MH370 and the aircraft registration 9M-MRO. And since then, 8 further items have been officially examined and determined to be almost certainly from MH370. In total, around 60 items have been found. And oceanographers from the University of Western Australia, UWA, and from the Commonwealth Scientific and Industrial Research Organisation, CISRO, have analysed the drift of these items of floating debris and confirmed that the origin was a crash location near the 7th arc between the latitudes of 28 degrees south and 36 degrees south. In summary, we have substantial electronic and physical evidence that MH370 crashed in the southern Indian Ocean close to the 7th arc and between 28 and 36 degrees south. In the next episode, we will continue tracking aircraft 9M MRO over the Indian Ocean, examining the available data and inferred flight path. We will be looking at the Jawn, Pine Gap, and Diego Garcia capabilities, the Whisper evidence, the search by the US Navy Poseidon aircraft, and the sighting by Captain Martin Smith, pilot of an Emirates flight across the Indian Ocean from Melbourne in Australia to Dubai in the Middle East. And these will be joint episodes with Jeffrey Thomas of Daily Airline News. So please leave any comments or questions you may have. We will address the key points in the next episode and publish responses on YouTube and on our website, mh370search.com. Thank you very much for watching. Please subscribe for future investigations.